Today we will be starting with a chapter named Units and Measurements. So before going deep into the chapter, we'll have some basics introduced to us. So first of all, we'll start with physical quantities. Now, physical quantities are those quantities which can be measured directly or indirectly, and based on these quantities we define the laws of physics. Now, physical quantities can be categorized or subdivided into two types: fundamental and derived. Fundamental quantities, as you can see, are those quantities which are independent of any other physical quantities. These are also called as the base quantities. Seven fundamental quantities that we are familiar with is length, mass, time, current, temperature, amount of substance and luminous intensity. And the SI unit are mentioned. So these are the fundamental quantities, and based on these quantities there are other quantities in physics that are derived from these fundamental quantities. For example, we have velocity. If you take the example of velocity, velocity is a derived quantity. The reason being, velocity is nothing but displacement upon time. Now, displacement comes from length, and t, as you can see, is out here, time. So velocity is not an independent quantity. It is dependent on the fundamental quantity, that is length and time. So this becomes a derived unit. There are other examples as force, which is also a derived quantity. It also is derived from these fundamental quantities. As we have seen the fundamental quantities and the derived quantities, now the derived quantities can be expressed as a combination of the fundamental quantities. Now the fundamental quantities are called the seven dimensions in physics. That is mass, that is represented by capital M, length L, time T, current A, temperature K, that is Kelvin, amount of substance mole, luminous intensity CD, that is candle. So these are the seven dimensions in physics. For class 11, we deal mostly with this 5. So these are the seven dimensions. The fundamental quantities are what we call as the seven dimensions. Now, for a physical quantity, what is dimensions for a physical quantity? So let us study this. It is actually the powers to which the fundamental quantities must be raised to represent that quantity. So in order to explain this definition, I will take the help of an example. So if we take density, that is one of the derived quantities, we all know that density is mass divided by volume. Now, for mass, the dimension is capital M. And for volume, we all know that volume has a unit, that is, it is either in cubic meters or in cubic centimeters. So the power is meter to the power 3. So we can always write meter means length. So it will be L cube, because the dimension for length is L. Now if the denominator goes up, we have M L minus 3. As you can see, there is no time in that expression. You can always say that t is 0, t0, that is 1. So this becomes the dimensional formula for density. Similarly, if you take another example, that is force, which is quite important. Force is nothing but mass into acceleration. You all know the second law of Newton. So, it is very easy if you know the unit for acceleration. It becomes very easy. For mass, the dimension is capital M, mass. Now, what is the unit for acceleration? The unit for acceleration is meter per second square. We all know this. Now, meter means length again, length. And second square is t. Right? Now, this can also be written as ms minus 2. So, for m, that is mass, we have capital M as dimensions. For acceleration, it is meter, that is length, and second, that is time minus 2. So this becomes the dimensional formula for force. Now let us come back to this definition. The powers to which the fundamental quantities must be raised. As you can see, these are the fundamental quantities and they are raised to a certain power. Right? Length is raised to power minus 3. Mass is raised to power 1. So these are the dimensions 1, minus 3, and for time it is 0. So these are the dimensions of mass, length and time in the physical quantity, that is density. But as a whole, we will call this as the dimensional formula for density. We try to calculate the dimension for gravitational constant and universal gas constant. For this, the equation that we will be using is the Newton's law of gravitation. F is equal to G m1 m2 upon r square. Now, we need to calculate the dimension for G. So, we will keep G on one side and all the quantities will take it on the other side. Now, the dimension for force, as we have calculated earlier, is mlt minus 2. For radius, it is, radius means length, right? It is L square. Now, as you can see, we have two masses. The m1 and m2 are the two masses. So we have capital M for this and capital M for this. So we have m into m, that is m whole square, m square. So it is power 1. So this will be 1 plus 2. If you take it in the numerator, it will be 1 minus 2. L is power 1, so 1 and 2. Same base, powers will be added, so 1 plus 2 gives me 3. And t minus 2. So we have m, 1 minus 2 is minus 1. L cube and t minus 2. This is the dimension for gravitational constant. Similarly, if you want to calculate the dimension for universal gas constant, we will use the equation, the ideal gas equation, which we are familiar with, that is PV equals to nRT, where pressure, volume, moles, this is the N, that is number of moles, and we have the universal gas constant R, and T is the temperature. So we need the dimension for R, so it will be PV divided by NT. Now out here, this is number of moles, So we already know that dimension is mole. T is temperature, that is Kelvin. For volume, as we have written it earlier, that this is LQ. Now this is P, that is pressure. So for pressure is simply force upon area. Now the dimension for force, we are already familiar with the dimension of force, that is MLT minus 2. For area has units in terms of meter square or centimeter square, as we already know it. So area is actually meter square, the unit for area. Or you can say area is length into breadth. So meter into meter square. So meter, the dimension is length, so L square, meter square, L square. So this will give me ml, that's power 1. So 1 plus 2 taken up, it will be 1 minus 2, so that gives me minus 1. And we have T as T minus 2. So this is the dimension for pressure. So we'll simply substitute all the dimensions. So P will be ml minus 1, T minus 2. So for P we will write ml minus 1, T minus 2. For volume it is L cube. This is number of moles. The dimension is mole. And for temperature we have Kelvin. Okay, remember this T is the dimension for time, and this T is that you have used out here is temperature. So the dimension for temperature is Kelvin. Don't be confused with that. So we have M. So we have only one. L, if you see, is the same base, power should be added. So minus 1 plus 3. That gives me L square. T minus 2. Mole, if you take it on the numerator, you have mole inverse. And Kelvin, if it is taken up, it becomes Kelvin inverse. So this is the dimension for universal gas constant. So here we will be starting with applications of dimensional analysis. Dimensional analysis simply means the method of studying the physical phenomena considering dimensions. So the applications of dimensional analysis are, the first application, there are three important applications. We will start with the first one, to check the correctness of a given physical relation. So with the help of dimensions, you can actually check whether a given relation is correct or not. So these are the two equations which we will deal with. So first of all, this is the expression, the first expression, that is for velocity. V is equal to root over gm by r, where g is the gravitational constant, m is mass, and r is the radius. So for the equation to be dimensionally correct, the dimension on the left hand side should be equal to the dimension on the right hand side. If they satisfy this condition, then only we say that okay, the equation is dimensionally correct. For the left hand side, it is velocity. So velocity, the unit for velocity, I have already said that it is very easy if you remember the units. So for velocity, it is meter per second. Meter per second, you all know this, meter per second. So meter means length, second means t minus 1. So this is much easier, that is the left hand side is L t minus 1. For the right hand side, root over gm by r, we can always write this as gm by r, root can be written as our half. So the value of g, or the dimension of g is, I have already calculated this value. So it is m minus 1 L cube T minus 2. So this is the dimension for G. For mass, we know the dimension is capital M. And for radius, it is length L. and entire to the power half. So if you see, this is m minus 1, this is m plus 1. Same base powers will be added, minus 1 plus 1 gives 0. Now L cube, we have L out here, so what remains is only L square. Out here we have t minus 2, so there are no other t's. We don't have any t out there, so we'll simply write t minus 2 power half. So this can be written as Lt minus 1 to the power whole square to the power half. Now this square and the root will be cancelled. So we have Lt minus 1. So here we can say that the left hand side, the dimension of the left hand side matches with the dimension on the right hand side. So this equation is dimensionally correct. Now let us solve for the other equation that we have. Now this equation is one of the famous equations that we use in an accelerated motion. So S is the displacement, U is initial velocity, T is time, A is acceleration. And this half, that is a constant. Constant do not have any dimensions. Constant like 2, 3, 4, they don't have any dimensions. So if you see it on the left hand side, it is S. So that is displacement, and for displacement you have, it is nothing but length. So L, displacement. On the right hand side, we have initial velocity. So for velocity, the dimension is Lt minus 1 for velocity, and for time t, we have dimension as t plus this half will not have any dimensions. For acceleration, it is meter per second square. So it will be, it is nothing but ms minus 2. So this will give me m, that is length, meter, s, that is t minus 2 time. So this is for acceleration. And again you have t square. So we have t square, time square, t square. Right? So if you solve it, what do we get? L t minus 1 t, that is t to the power 0. So we can skip that part. Out here it is t minus 2, t plus 2. Again, same base, powers will be added, minus 2 plus 2, again 0. So we have only L. Now L plus L is L again. Now this is a point where the students get confused most of the time. I'd like to explain this. For example, okay, so before explaining that, let me conclude with this. We have the LHS and RHS both have the same dimensions. So that means that this equation is also dimensionally correct. It is dimensionally correct. So let me explain how L plus L is L again. For example, if you add 5 meters plus 6 meters, you will be getting 11 meters, right? So the unit remains same. So there will be no change in the dimension. For example, if you have Lt minus 1 plus Lt minus 1, this will again give me Lt minus 1. Even if I have a minus sign out here, that will be at the same result, Lt minus 1. Because these are the units, and units does not change when you are adding or subtracting. For example, if we have 10 meter per second square minus 6 meter per second square, this will be 10 minus 6, that is 4, but the unit remains the same, meter per second square. So there is no change in the unit. So Lt minus 1 will be here, Lt minus 1. Even if it is plus or minus, it does not matter. It will be Lt minus 1 because the unit will remain same when you are adding or subtracting.